Welcome to this explainer. Today, we're tearing down the hype and looking at gRPC versus REST and uncovering the performance truths that nobody really tells you. Let's jump right in by looking at the staggering scale of modern distributed backend architectures. If you're building software today, you know we've largely transitioned away from those old monolithic structures and moved straight into hyperscale microservices. But, with this shift comes a hidden cost that isn't always discussed. We aren't just writing code anymore. We are managing the physical reality of network physics, serialization, and protocol handshaking. To really grasp the performance battle between gRPC and REST, we have to start by looking at what actually happens when microservices communicate at a massive scale.
To put that scale into perspective, consider this jaw-dropping number, 30,000. In a contemporary high-performance environment, think of an app like Uber. A single ride-hailing request initiated by a user on their phone can traverse around 500 discrete services and trigger over 30,000 remote procedure calls, or RPCs. No way, right? But it's true. When your system relies on this level of interconnection, every single microsecond of latency is multiplied thousands of times over. This is what we call the network tax. When systems exhibit these super chatty communication patterns, the choice of how those services talk to each other becomes the absolute primary bottleneck for your entire infrastructure.
So let's dive into Section 1, under the protocol hood, escaping the HTTP/1.1 bottleneck. You see, traditional REST architectures predominantly rely on HTTP/1.1, and well, HTTP/1.1 suffers from a pretty major mechanical flaw known as head-of-line blocking. Imagine a single-lane highway. If a large, incredibly slow-moving truck is at the front, literally every single car behind it is stuck, regardless of how fast they could potentially go. In a REST API, if a client sends multiple requests over a single connection, and that first request requires some heavy database processing, all the subsequent requests are just sitting there, stalled, waiting for that first response to clear. It basically creates a massive traffic jam.
The industry's shift toward gRPC fundamentally fixes this traffic jam. gRPC is built upon the much more modern HTTP/2 transport layer, which introduces a game changer, multiplexing. Multiplexing allows multiple concurrent requests to be interweaved over a single TCP connection all at the same time. So instead of our single-lane highway, we now have a highly coordinated, multi-lane freeway where requests and responses flow completely independently, tagged with stream identifiers. This entirely eliminates the need for those costly, repetitive TCP handshakes that HTTP/1.1 demands for parallel connections.
When we compare the mechanics side by side, it's pretty eye-opening. REST, on the left, gives us simplicity and ubiquity. It uses text-based, human-readable JSON payloads over HTTP/1.1. Sure, it's super easy to debug, but as we just saw, it's prone to blocking. On the right, gRPC sacrifices that human readability for raw, unadulterated machine efficiency. It leverages that HTTP/2 multiplexing we talked about and uses protocol buffers, or protobuf, which is a highly efficient, strongly typed binary format. You define a strict contract between your services, and the data is sent as raw bytes, completely stripping away the bulky field identifiers you'd find in JSON.
Moving right along to Section 2, latency and throughput benchmarks. Hard data on speed.
The raw performance numbers here are absolutely wild. In academic-grade tests that push systems to their absolute limits, a standard JSON and HTTP REST setup handled roughly 3,480 requests per second. But the gRPC setup, utilizing protobuf and HTTP/2, it handled approximately 8,700 requests per second. That is nearly 2.5 times the throughput on the exact same hardware. When you're processing millions of events, that difference translates directly to fewer servers, way lower cloud computing bills, and a much snappier experience for your end users.
So what's driving this massive throughput increase? A huge part of it is data size. Empirical evidence shows that gRPC reduces payload sizes by over 70% compared to REST. To put that into perspective, a simple request that takes up 69 bytes in plain text JSON can be shrunk down to just 20 bytes when serialized via protobuf. Multiply that tiny saving over millions of requests, and that is an incredible amount of network bandwidth saved.
And because protobuf creates these compact binary payloads that are literally 5 to 10 times smaller than JSON, you aren't just saving on network transmission latency, you are also saving heavily on CPU cycles. Think about it. Parsing a text-based JSON file requires the server to read strings, look for brackets, and map types dynamically. Protobuf is pre-compiled binary. The CPU simply maps the raw bytes directly to memory.
It's an absolute game changer for computational efficiency.
Let's look at Section 3, the power of streaming, beyond the request-response model.
Here's the thing. REST is inherently built on a single request-response model. It completely lacks native streaming capabilities. If you want real-time data with REST, you have to engineer clunky workarounds like long polling or basically bolt on entirely different protocols like WebSockets. gRPC, on the other hand, was built specifically for this. It offers native streaming support right out of the box. You can have client streaming, server streaming, or even bidirectional streaming, where both the client and server are firing off streams of messages simultaneously over a single persistent connection.
But let's take a reality check in Section 4. Real-world production gotchas. The hidden network taxes.
In the real world, modern microservices rarely talk directly to each other, right? They communicate through service meshes like Istio, utilizing sidecar proxies like Envoy to manage traffic and security. Well, these proxies add their own latency. Benchmark tests on Istio show that at 1,000 requests per second across 16 connections, the proxy adds about 3 milliseconds of latency. But scale that up to 64 concurrent connections, and Istio is adding 12 extra milliseconds of latency. When your request has to hop through 15 different microservices, those 12 milliseconds compound incredibly fast. It can potentially wipe out all the speed gains you got from switching protocols in the first place.
So a crucial point here is how you actually configure that routing. REST forces you to use Layer 7 routing because proxies need to parse the HTTP headers and JSON to make routing decisions, and that parsing takes time. Because gRPC uses efficient multiplexing, you can often push its routing down to Layer 4, the TCP layer, which is protocol agnostic. In complex multi-hop architectures, bypassing that Layer 7 parsing overhead and using Layer 4 for gRPC yields about 53% better response times.
But it's not all sunshine and rainbows. Despite its blazing speed, gRPC introduces some real operational friction. First off, it completely lacks the native HTTP caching mechanisms like eTag or cache control that REST relies on to offload database reads. Second, standard web browsers cannot speak raw HTTP/2 gRPC natively. You absolutely have to run a translation proxy like gRPC Web to use it in a front-end web app. Furthermore, in production, default mesh configurations can cause absolute chaos. For example, Istio defaults to retry all 503 unavailable errors. This means you could inadvertently flood a struggling gRPC service with a massive retry storm if it intentionally returned to 503, which, let's be honest, is always a super fun page to get at 2 a.m. Plus, your team actually has to learn to write and manage protobuf contracts, which definitely has a steeper learning curve than simple JSON.
Which brings us to our final section, when REST is actually better, the pragmatic choice.
As engineers, we have to be pragmatic. Use gRPC where its strengths truly shine, for heavy internal backend microservice-to-microservice communication, and for bandwidth-constrained environments like IoT devices or mobile telemetry, where those tiny payload sizes are absolutely critical. But stick to REST for your public-facing APIs and standard browser clients. In those scenarios, universal compatibility, ease of developer onboarding, and native HTTP caching are way more important than squeezing out a few extra milliseconds of throughput.
So, as we wrap up this explainer, I want to leave you with this final thought to chew on. As you evaluate your own backend architecture, take a hard look at how your services are communicating. Ask yourself, are you strategically using the right protocol for the specific job at hand, or are you just paying a massive network tax out of habit? Carefully weighing these performance truths is exactly what separates good infrastructure from truly great hyperscale systems.